So next up, we've got Hal Rosenstock from Mellanox giving us an update on the Scalable SA project.
So for those of you who were here last year, you heard about the start of the Scalable SA Project. I guess SA, that's an acronym. For those, maybe, hopefully most people in this room know, it's Subnet Administration, part of the SM, or associated with the Subnet Manager. And this is going to be an update on the progress that we've made since last year when Sean kicked it off and reported here. So we're going to start with going over what the generic problem is. You've heard this from Bob from NASA. This is only one of the hot buttons that he mentioned. A number of things in terms of SA, but it all comes down to n-squared loads on the SA, where all nodes want to talk to all nodes, and there are a number of n-squared problems, and SA was defined and implemented as a centralized entity. So there are other n-squared problems that limit the performance for things like RDMA-CM, things like name resolution or address resolution, and this can help solve those problems as well, and I'll talk a little bit about that. So in a large subnet, we have approximately 40,000 nodes. The SM database comes out to be about 500 megabytes for this. If you just do a rough seat of the pants, one path record, 40,000 nodes squared, you get a 1.6 billion path records. For the SA to calculate the path records from the SMDB, we've done some analysis. It would take about an hour and a half. At a communication rate of 50,000 queries a second, it would take 9 hours to get them out to all the nodes one at a time. You've heard about this from Bob in a different way, with some other problems added on top of that. So what we've done with SSA is we've taken the SA, we're distributing the SMDB down as far as that access layer. The access layer does the path record computations for all the clients and distributes the path record databases into the client, and it's a local lookup in the client to get the path record. So every client has, just doing another seat of the pants calculation here, one path record to every other 40,000 nodes is about 2.5 megabytes or something like that. So it's not a very big deal, and we'll talk about other things that we've done in the distribution tree to optimize the client to not, for CPU utilization, not interfering with a running MPI job. Okay, so we built the distribution tree out of RSocket's AFIB support. AFIB went into the kernel, I don't know, last April, last May. There's tree building code here. The parents selected on some nearness criteria based on hops, and some balancing based on the fan outs at the different layers. So this is just a slide showing some of the preliminary, no tuning, just send receive, not using RDMA on a certain Xeon core machine. Moving half a gigabyte of data takes about 2/3 of a second. The number of management nodes that you need in that tree that I showed is dependent on the subnet size and the node capabilities that you're using for this. We also added in a feature that we call combined node support, where you could, for a smaller network, if you wanted to deploy this, you could combine different combinations of the layer in one node. So you can use this in, you can play with this in smaller networks if you don't want to dedicate host to the distribution tree. So the fan-outs in the distribution tree for a 40K node compute node subnet that the goals are 10 at the top layer between the distribution and the core, 20 between the access and the distribution, 20 access nodes per distribution node, and 200 compute nodes or consumers per access node. So that gets us the 40,000 compute nodes. So the core layer is co-resident with the SM. It supports SM. It will support SM failover. The core is found at the SM lid. When nodes come up, they request to join the tree. They're joined into the tree by a MAD protocol, an application. I think it's an application-specific class that's used for that. The tree balancing code figures out who the parent is. It queries the SA for a path record between the joining node and its parent, gives it to the, returns that to the joining node. The joining node then creates an RSocket connection to its parent. The tree forms and the database is pulled down the tree. At the SM level, it extracts and compares from the, I'm calling it the raw SM database, what all the data structures in the SM itself are, to the set of information, to the SSA form of that. And right now it only supports path records, but in the future it can do more. The tree balancing code is also responsible for rebalancing, and there's a fault protocol when nodes fail, connections drop, and nodes have to get reconnected. These are some early preliminary comparison, extraction and comparison numbers for how long it takes to do the extraction and comparison at the in the core layer. The distribution layer is really just taking this SMDB that's being passed down the tree and fanning it out for the next layer. So it's like a multiplexing layer. It doesn't care about the database, what the contents are. It's abstract. It can support multiple databases, so we could extend it for other kinds of data that don't necessarily come directly from the SM. That might be an application for some things that Todd and Ira are going to talk about. There's data versioning via some epic that says when the database has been updated, and there are incremental changes that are supported in the distribution via this transaction log. So the access layer is another layer. This layer has a lot of compute requirements because it takes the SMDB and converts it into what we call the PRDB. So there's an individual PRDB so this is, the blue dots are showing access layers, and this access layer happens to be connected to the core layer. So, and these are all the compute nodes. So the access layer computes a PRDB that's particular to each compute node, and it gets transferred over RSockets into the ACM cache in that machine. There are Right now, there are 4 or 5 caches. You can go name to path record. That supports a little sketchy and getting filled out. The main ones that are used are IPv6, directly to path record with intermediate steps, IPv4, GID, and LID caching. So you can look up by LID, GID, IPv4, IPv6 addresses, and never have to go outside your node. So that's going to basically multiply, path records, when they change, they get recalculated at the access layer and re-pushed into the ACM. That only happens at when the compute node requests that at MPI job startup. So it's potential for, there to be stale records and connections timing out if something's changed, but that would have happened anyway. So it's at the access layer to the compute node, the access layer will update the epic in the compute node for the PRDB saying there's a change pending, and when the next query comes on somebody trying to do a resolution, which only happens at job start time, it'll pull the database, update the database, and then it gets all fresh, updated PRs with it's an insert, modify, remove that occurs. At the access layer, we've made this computation that goes from SMDB to PRDB into a multi-processor element computation. So it takes advantage of multi-cores and multi-CPUs. And we've looked at this and done this on a 16-core machine, and we've seen that it multi-threaded, it almost is linear. It's not going to be quite linear. We have some ideas on how to improve it to make it even faster. So this is a scheme that takes that all RDM ACM-based applications can take advantage of by running ACM. And so what the difference for people who are familiar here between the existing ACM and this is real. You can view this as a back-end change. So ACM version 1 used a set of multicast overlays to basically bypass, to construct path records and do ARP-like operations over MADs as a way to get this information. But with SSA backend, it comes down this distribution tree, and that's how it gets all this information. And because of that, I think you're going to hear what's going to happen with ACM architecture is going to change from what it is today. In the future, we'll be able to publish things like host names and IP addresses and distribute that. And other ACM things we're looking at is a more efficient cache structure than what's currently implemented in ACM. We're debating whether to use a single underlying path record cache for those different caches that I talked about, name and IP address, GID and LID. You can combine different layers in the tree. So you can run core and access together. You can run distribution and access together. So you can essentially do this with one node and a set of compute nodes in a really small environment by running core and access together and bringing up ACM. So it all depends on, you know, what the scale of your network is and how you want to put it together. For reliability, there's tree rebalancing and reconnecting, and this is work to be done. There are primary and backup parents, and also there are some, so the main cases are SM failover and also connection failover, and these are the next steps with SSA. What are the system requirements here? You need a pretty recent world in order to do this. You need a AFIB capable kernel. So that's in 3.11 and beyond. You need lib RDMA with AFIB and keep alive support, and some bug fixes that went in beyond the 1018 release, which is the most recent release a couple of months ago. It doesn't really care about lib-IB verbs version. There's nothing special about that. Lib-IB UMAD is beyond using the latest stuff in the upstream Git tree, which is beyond the last release, 139. OpenSM is 3317 or beyond, that being the last release. In addition, so AFIB is supported, so you need an AFIB is supported in some lib RDMA CM examples, but the first real application recently added code to be able to use this, and we've only exercised, it's in its early days, but OpenMPI now has, you can run with the RDMA CM connector and build it for AFIB support and use SSA to make your connections. So it uses the scheme. So to deploy it, there'll be a core package, a distribution package, and ACM is shipped by the distros, and I don't know if there's a talk about how ACM is going to change in the future. The project team, I'm the maintainer, Sean and Ira from Intel, Susan from Llano, Ilya, Sasha, Lenny does the verification. At Mellanox, Vladimir is the manager, and Eitan does architecture. The main switch is most of the development in the last, 6 months has switched over to Mellanox. There's review by the rest of the project team, and as I said, there's some verification and regression ramping up on this as well. The initial release is going to support path records. Limitations that it's not going to support are things like QoS routing and policy that's supported by OpenSM, things like Taurus support, and also virtualization isn't initially supported. Those will be increments that'll be added in later. We expect to have a preview release by the end of June, and our first official release by the end of the year. Future developments would include IP address and name resolution. You'll hear more of the application-facing side stuff for this soon from Ira. And there are many other possible uses for this that can be done. So in summary, this turns a centralized SA into a scalable distributed SA. It works with existing apps that use lib RDMA-CM with minor modifications. It's going to be a fault tolerance scheme. Please contact us if your site is interested in deploying this. We know, so far we have one site that we know is going to be an early adopter of this. We'll be moving into that site to prove out the fan outs and fine-tune things in a little while, shortly. So that's all I have, and I don't know if there are any questions.
Maybe I missed something, but how will the request be treated? I mean, when the client will request the SSA infrastructure, which node will respond? How will it be selected?
So I'm not sure I understand what requests the.
When there is a request from a compute node for an address, a peer request, which node in
The compute node itself responds, will have the path record in its cache, and either will be able to respond or say there's no path record. The question was, when a compute node makes a request for a path record, who returns the path record, where that occurs, and that all occurs between libRDMA-CM and the ACM. The path records are kept in the ACM caches, and they're fully populated, so the path record should get returned directly out of that with across. Right now it's a socket, and maybe it'll change. There's some discussion about that, potentially. The scheme to go from the application, which uses libRDMA-CM, to the ACM currently uses a socket-based communication. That may change to shared memory. So, other questions? I thought there was another question. Okay, thank you.